Essentials for a machine vision lighting lab. What lights do you need to build a testing lab? So this is what we're going to be answering throughout the webinar. You're not going to always have the perfect light for every application in your lab, and it's not even really possible to have a lab that comprehensive. Even CCS with, the access we have to our huge inventory, we don't always have the perfect light. So what we want is our lab inventory to be comprehensive enough that we can come up with the solution from the lights that we have. Obviously, though, the more lights you have, the easier testing becomes. So the idea really is to start with the basics and build it up over time as you learn which lights you tend to recommend the most, or do you often wish that you had a larger ring light of some kind, something like that. So you're building it up to be tailored to what you need, but you started with the basics to solve most of your applications in the beginning. So we want this webinar to provide more of a direction to help if you're just, starting to build a lab or if you only have a small one, that the lights we're picking are optimal for the applications that we come across and are typically trying to solve. The applications can be split up into two different categories. So there's precision and flood. And precision lights are for applications that aren't necessarily obvious for the camera to see by just placing it underneath the camera immediately. So in order to highlight the defect or the detail, it requires the light to come from a specific direction, maybe a specific light working distance, or wavelength, something along those lines. So in order for the camera to see the detail, it has to have the perfect setup, essentially. Floodlights and floodlight applications on the opposite are kind of the opposite, where the application is much more straightforward. It's often something like reading a black barcode on a white background, and we just need to provide an even and uniform image that looks the same every time so the camera can process it quickly. These also tend to be large field of view applications or long light working distance applications. And the reason that we need to understand the difference between these two types of applications is because a light from one group will not solve the application in another group. For example, if you say, yes, I have a ring light, it's a flood ring light, I can solve all my ring light applications. That is not the case. A flood ring light will not solve an application that requires a low angle ring light to see the defect. So when we're thinking about what lights we need in our lab and we have to think about what applications we tend to solve. We tend to need to solve. Are they hard and they require, that perfect setup to get the right image, or is it usually pretty straightforward and you just have to get an even uniformity? Whatever it is, kind of build your lab with more of those lights in hand, more precision or more flood. If you're like CCS and you come across both types pretty evenly, then you want to get a variety of flood and precision lights so you can solve every application as it comes across. So we have our two types of applications, but kind of regardless of what type it is, all of our samples will have the same properties that we have to consider. We have to think about the reflectivity of the sample. Is it more diffuse or is it more reflective? The texture of the sample, is there a lot of texture or not? Are we trying to hide the texture or enhance the texture? And the color of the sample. Can we use a colored LED to create more contrast? So if all of our samples have those three characteristics to factor in, then we need to make sure that our lab lights have enough range to react properly with those characteristics to solve the application. And these lighting principles that we're going to go through that we use to think about how to interact with our properties is the direction the light's coming from, the wavelength, the amplitude, and the polarization. And we did do a whole webinar series on how we use this way of thinking to solve applications. So that QR code in the bottom right will take you to all of those videos. Throughout this webinar, though, we'll touch quickly on what each principle is, but if you want more in-depth information, please go watch this series. It's a really unique way of thinking about how we solve applications, what light we're capturing instead of just this light solves that application. So on to our lighting properties, starting with our direction. The first direction we're going to focus on is bright field. And bright field is when the light is reflecting down onto a sample and then being reflected off that sample, and most of it is going directly into the camera. That's when you get all of that white background. Anything that appears dark, it's when that light hits that surface and it scatters out. Not enough of that scattered light reaches the camera and it appears dark. So the lights that we need to have in our lab to achieve bright field images are bar lights, ring, coaxial, dome, and panel. Bar lights are great for a lab because they're extremely flexible. You can place it at any angle to match that reflection that you have if your camera is set off to an angle as well. They can be, if the camera is aligned straight down, you can have multiple of them to improve your uniformity. Having multiple bar lights in a lab is always going to help and not hurt. Panel lights are this way as well, and especially since they have a larger emitting surface, they tend to provide a more uniform image, especially on really highly reflective surfaces. When the camera is set up to be, shooting straight down, inline lights like the ring, coaxial dome, and panel with the camera hole work really well as well. Ring lights are a lot more straightforward because they provide a really uniform illumination, but they're also really easy to diffuse and to polarize. And I will get into the best time to use a dome, coaxial, and panel light in a few slides. So the next we have is dark field, and this is essentially the exact opposite of bright field. That light is still reflecting off that surface, but instead of the camera capturing that direct reflected light, the camera is now capturing that scattered light. So that's why the text is now appearing as white, and that surface, that highly reflective surface, is appearing as dark. So the lights we need to achieve dark field images, once again, the flexibility of the bar light really shines through because it can work as a low angle light as well. You just have to place it at a shorter light working distance off to the side and aimed into the sample, and you can get a really nice low angle image. The other lights that kind of come up when we are trying to get a dark field image is low angle ring lights. And these are a little bit harder for labs because with other lights, having a larger light, but you want it to be smaller, you can kind of block off a bar light to make it smaller to see what size you need. But with a low angle ring light, you can't really change the size that it is. You can't make a low angle ring light that you have bigger or smaller like you can with other lights. So unfortunately in labs, ring lights, specifically low angle ring lights, you kind of have to have more, not just one big one, but more of different sizes. Because if it's too small, you'll get hot spots around the edges. It won't be a uniform image. And if it's too big, then you won't be able to see enough of the center that you're trying to see. So that's kind of the downside of low angle ring lights, is you have to have more of them in your lab to solve these applications properly. So next we have to talk about, for the direction, is the dome light or the shadowless light. And the point of a dome light or a shadowless light is to remove 3D texture from your image. Essentially, the idea is that you're sending light down from every direction, so you don't have any shadows, and therefore, to the camera, it looks like a flat surface, even though there is technically texture to it. And the lights that we get for this texture removal that we want to have in our lab are standard dome lights, a panel light with a camera hole, and a flat dome light. So the standard dome lights are the most diffuse. They're not necessarily as intense as the light is reflecting off of the dome shell and onto the surface. And a panel light with a camera hole is less diffuse because the light is directed straight down from the LEDs. But this light is more ideal for providing a uniform image, especially in a large field of view application or applications with a longer light working distance. Both of these lights have a camera hole in them, which actually limits how far the light can be placed from the lens in the camera before that camera hole that's pretty small starts to interfere with the image. A flat dome light, on the other hand, aka the LFX-V, the camera looks through the acrylic plate, and so we have a lot more flexibility on where it can be placed within the working distance of the camera. But one thing to note about that is as you adjust the light working distance, the image will change. The closer you are to the sample, the more of the dome effect, which is removing texture, you're going to have. And as you move it further away, the LFX-V will start to actually show those height changes. One downside of the LFX-V is sometimes a dot pattern effect can kind of cause a problem with the image. It's not too often that it really does make it where you can't use that light, but every once in a while it happens. So really the takeaway here is for your lab, it's good to have all three options so you kind of have all your bases covered. You've got the flexibility in the light working distance, the size, and the effect of the dome light itself. And last but not least, what we have to consider when it comes to the direction of the light is the collimation. And the collimation is essentially, if you take a point on your sample, the angle at which the light hits that point is what we call the degree of collimation. We think backlights come out more straight, but they always come out with like a diffuse light comes out in every direction. And so we always don't get those sharp lines that we think we will because there's a point where the light can hit the sample and reflect into the camera. So what we want to do is find ways within our lab that we can change the collimation of our lights or use it to our benefit. Um, Backlights are the lights where collimation is most obvious and apparent. And this happens when we can put light control film on, which essentially blocks all the light coming out in, you know, every direction and only lets the light that's shining straight up through. So the backlights are the one where collimation is most obvious. And they can come with light control film built in, or it can be an accessory that you add on. And for a lab setting, I definitely recommend opting for the accessory option. That way you have the ability to test the backlight as a standard backlight. You can test and see if the light control film is needed or not, or if even only one direction is needed. Sometimes having just the horizontal light control film is what solves the application, and the vertical one hinders it. So having that flexibility with your backlight is always useful to have. Coaxial lights and flat dome lights are for front lit, bright field applications like we've gone through. And when I described the LFXV in the last slide about creating different images at different light working distance, that's because of the collimation of the light. We're changing the angle at which it's hitting the sample, so it's highlighting those 3D textures instead of hiding them. The coaxial light is more collimated than the LFXV due to how it's designed with that backlight coming through. It hits that half mirror and it's reflected down in a more parallel way. So it does do a better job of making the height changes more apparent, but they do a similar job between the coaxial and the flat dome light. It's kind of like a Venn diagram with a small overlap. It's enough that sometimes either light will work, but not enough that you really would have one light but not the other. So for your lab, it's good to have a backlight, accessory for light control film, a coaxial, and a flat dome to factor in the collimation and use collimation to your best benefit. So next we have to talk about the wavelength of the light and how we can use this to solve our applications. In the visible spectrum, we can use the wavelength of the light to essentially create more contrast. If you have sunlight shining down onto a sample, a red object will reflect red, a green object will absorb red, reflect green, blue absorb red, reflect blue. So if we shine only a red light onto these objects, the red object will continue reflecting the red light, and green and blue will continue absorbing the red light as they did before. And now if we take this scenario and image it with a monochrome camera where we're capturing light, the red object is going to appear white and bright to our camera, and the green and blue are going to appear dark. And in some scenarios, like a metal bearing, it's not going to matter. The blue light, the green light, white, red, they all provide the same image. But you can't just say, oh, it's metal, light doesn't matter, because sometimes it does. So you can see here with the solder balls, the blue light and the red light really didn't make a difference. But for the gold pattern here, the red light enhanced it and the blue light hid it. So depending on what we're trying to get out of solving this application would depend on which color light we choose. So now that we know that color matters in our lab, which color lights do we need to have in our inventory? And there's 4 ways that we can kind of change the wavelength or use the wavelength of our lights for solving applications. The first one is a white light with a bandpass filter. So essentially what this is doing is shining down the full spectrum, but the filter is blocking out most of the spectrum of the LED except for what it's allowing to pass through to the camera, effectively creating, in this image right here, a blue light. Monochrome light is when you have the light and all of the LEDs are just one color. A full color light is different than an RGB light. So full color light is when one LED can do red, green, or blue. And so every LED is a full color LED, as opposed to an RGB light where they essentially switch off which LED they place. So they'll do a red LED, then a green, then a blue, a red, then a green, then a blue. So all of these lights have pros and cons to them, and they have kind of a time and place for the lab itself. So the white lights of the bandpass filter, I actually really prefer this in a lab. It's a really cost-effective way to test the wavelength because you can set up your light, your white light, and you can leave it set up. You don't have to change any lights, and all you have to do is replace the filter that you have, and then you can tell if the color of the light will improve or make worse your image. So it's really easy to test the wavelength while keeping the setup, and you don't have to have, you know, of the same light, multiple different colors. The downside to this, though, is you're actually not able to test the intensity of the light since we're taking the whole spectrum and blocking out about 80%. We don't know if we purchase a, blue ring light, is that going to be bright enough? For most of the applications you come across, you probably don't have to really think that hard about it. But if you're at a point where it's a high speed application and you need to make sure you have enough intensity, this isn't necessarily the best method to test for that intensity. On the other hand, monochrome lights, which is where you just purchase, that blue ring light, that is where we can confirm the intensity because that's going to be the light that you purchase and install in your machine. The downside to, having multiple lights of different wavelengths is that you do have to have more of them on hand. It's a much higher cost to be able to check if the wavelength will affect your image or not. Full color lights, the benefit of them is that kind of the same as the white light with the bandpass filter. It's really easy to test the wavelength while keeping the setup. All you have to do is plug in different channels and it will turn on the different colors. And you can also test multiple wavelengths at once. So you can have the red channel and the blue channel turned on, and you can see if that magenta color will make your image better or not. With the white lights and a bandpass filter, you aren't really able to double up the filters. You would have to get a magenta bandpass filter, which they do exist, so it's not like that's not possible to do. But that's just kind of the difference between them. The cons of a full color light are the same as the white light, the bandpass filter, as you're only using a third of the LED at a time. It's going to be less intense than a monochrome light, and it's not a good test of a true white LED. A white LED has a spectrum that's kind of got a big peak at blue, and it drops down and then goes up a little bit and pitters out around, the IR wavelength. And when we turn on the red, the green, and the blue LEDs in a full color light, it's going to appear white to our eyes. But the spectrum of that is a big bump at red, a big bump at blue, and a big bump at green. So it's not the same flat kind of full spectrum that you get. Most of the time, not really a problem, to be honest, unless you're doing really specific color matching or something like that. You can kind of get away with turning on all three lights and being like, yep, white won't really change my image either. On that kind of same note, the red RGB light, similar pros, pretty much the same pros. You can test the wavelength while keeping the setup, and it's easy to test multiple wavelengths at once. The downside to an RGB light is the poor uniformity. So because you're turning on every 2 or 3 LEDs at a short working distance, you're not really going to have that good uniformity on the light. As you move it further away, it'll only get better, but that's kind of the downside to these lights. And they also are less intense because you only have every, one or every third LED on, for example. And same principle of it's not a good test of the true white LED. So when it comes to our lab, my overall suggestion is to, if you're trying to be budget friendly, get mostly white lights with the blue filter, with a good filter kit, 1 or 2 full color lights, so you kind of have that option as well. And then as you expand your lab, especially if you're getting, another LDR2 ring light, then maybe get that one in a monochrome light if you kind of find yourself, okay, I recommend a red ring light a lot. I should probably get one on lab just to have on hand. So when you're just doing the basics, mostly white, few full color, get monochrome lights as you start to expand. Now getting into the invisible spectrum, using the IR wavelength to solve our applications. The IR wavelength, or the infrared wavelength, is really unique because it has a high transmission rate, which it allows it to pass through certain material and remain unchanged and still hit the camera. So in this example here, we're seeing soy sauce. A white light, when it hits the soy sauce, obviously can't penetrate through. So we see what would probably be a good fill level application. But if we're trying to see foreign material within the container, it wouldn't work well. But that IR light can pass through that soy sauce, remain unchanged, and if there was some type of foreign material in here, we would be able to see it. When it comes to having IR light in a lab, it's not as critical to have it in every single form factor, but it's more critical to make sure that you have the right wavelengths to check with. So the kind of industry standard wavelengths that you find are around 850, 860, 940, 950. And between 850 and 860, that's not going to change your image too much. Same thing between 940 and 950. But between, an 800 and a 900, that might actually affect your image. So typically you want to have at least one light that starts with an 8 and at least one light that starts with a 9 in your lab. You can kind of use the form factor in the visible spectrum to make sure that, okay, yes, this coaxial light is solving the flatness of the image that I need it to do, or the dome light is providing the flatness of the image that I need it to provide. But I want to know if I can remove the text or the print on this blister pack, for example. You can just shine the IR wavelength on it, and if the text removes, then you can assume, okay, the flatness of the dome light with the wavelength of the IR, I can get an IR dome light and my application will be solved. So that's why form factor isn't as critical, but having a good variety of wavelengths is more important. Next, when it comes to UV lights, what lights do we need for our lab? So the idea of using a UV light in machine vision is to capture the fluorescence phenomenon. And that's essentially when we have some type of property on our sample, whether it's invisible ink or, part of the sample itself, in which you shine a certain wavelength on, most of the time it's 365 nanometers. And when that wavelength hits that invisible ink, for example, that invisible ink excites and reflects a light off at a higher wavelength, usually around 405 or something like that. So we can utilize that in our lab to create contrast in a lot of different ways. The 365 is the most common UV wavelength, but there are technically you can 385, 395, and 405 can be considered UV as well. For the lab that light I would recommend is the 365 nanometer pure UV technology. So what pure UV does is it takes the UV cut filter, which if you have your light shining down and your fluorescence, like in this image here, we're seeing both the shined light and the fluorescence, but the shine light is interfering with our image. If we put a UV cut filter, that's essentially saying we don't want to see any light less than 400 nanometers, so we're blocking out most of it, but we're still seeing what's fluorescing. But there's going to be just a little bit that can kind of sneak through here at the end, and that's that glare we're still seeing. So the pure UV technology kind of cuts out that little tail, so all we capture is the fluorescence wavelength, and we can get a nice high contrast image without any glare. Pure UV will not hurt any application that you're solving, even if the application doesn't require, it's not a high glare, you just need a UV light. It's still 365 nanometers, so it's still gonna fluoresce or not fluoresce the material that you're testing. But it will only help if you are testing a highly reflective sample. So for your lab, I would say 365 nanometers in the pure UV. And once again, same as IR, the form factor doesn't matter much because you're kind of just seeing, does this fluoresce or does it not? They actually don't even make UV light in that many different form factors. So next we're going to talk about the amplitude, and by amplitude we mean the intensity of the light. So sometimes applications have really high speeds, and so we need to get more light and to get a good image in each picture that we're taking. To do that, we can overdrive the light, but we want to be able to test that we can get enough light when we're in our lab. So we don't want to assume, yeah, I can overdrive it and it's good to go without knowing how much we have to overdrive it to solve the image and have enough light. So there are two ways that we can get more light for a shorter period of time. And the first is by using an overdriving controller that can take our standard intensity lights and can pulse them at a higher intensity for a shorter amount of time. The other option that we have for getting more light in an image is to get a dedicated strobe light that is essentially made and manufactured to only strobe, but be brighter than the overdriving controller and standard light setup, better than that can achieve. So how do we kind of know when we need to overdrive, when do we need a dedicated strobe? That comes down to the exposure time of the application is the general rule. So if your application's at around 500 microseconds, for the most part, standard overdriving should work. It does depend on, what we're looking at, what light we're using, what defect we're solving, stuff like that. So it's not a hard and fast rule, but for the most part, around 500 microseconds, an overdriving controller with the standard light's fine. Between 500 microseconds and 100 microseconds, that's when you could kind of do both. It's situational. The dedicated strobe light might be your best bet, or overdriving is still sufficient, and it's hard to say. Once you get down to around 100 microseconds or less, then you're pretty much locked into a dedicated strobe light. So pretty much for your lab, for basic labs, we would say an overdriving controller is going to be sufficient. That being said, if you have a lot of applications that are, around or less than 500 microseconds, it might be worth it, the investment, for you to get a dedicated strobe light to test with. If you're interested in learning how to test high-speed applications, how we kind of go about it when we usually have a limited number of lights that are dedicated strobe or something, we did do a case study on how to test high-speed applications. So scan this QR code, it'll take you to the page, and you can kind of read through the steps we take to make sure that we can reach the short exposure time if an application requires it. So pretty much last but not least, we want to talk about the polarization of the light. So polarization of the light, we have a whole webinar about removing glare, removing unwanted glare from an image. And then in that webinar, I get into what polarizing is done, what other methods do we use to remove glare. So focusing on how we use polarizers in our lab, essentially what they do is they just block the direct light and they let through the scattered light. And so we need to make sure that the lights we have a polarizer on them, but it also has to work in tandem with the polarizer on the camera lens. And then those have to be aligned vertically to each other. So most bright field lights will have a polarizer accessory. The dome light doesn't, but by nature it removes glare because the light comes from every direction. So for your lab, make sure you have a good polarizer for your lens, but also make sure that if the bright field light has, or any light, if any light comes with a polarizer accessory, then get that for your lab because it's probably going to come in handy eventually. So that is kind of all of the properties that we've talked about and what lights we need to solve them. So now that we've talked about the types of lights a lab needs for each principle, we're going to go talk about the specific light that we think are good for most general labs. And this list is on purpose very general, so it might not be the perfect list for your lab. So there are some things to consider when you're kind of making your own list based off this webinar. So honestly, you might disregard certain recommendations that I'm saying if it doesn't really apply to your specifically your typical applications, and in the end, get what's right for you. So for example, if your applications are larger, focus on floodlighting. If they're at a higher speed, add that dedicated strobe light to your line. And if you have to, most of your applications tend to have square samples, then get a square low angle bar light instead of a ring, or even add more bar lights to your lab so you can make a square for better uniformity, stuff like that. So take what I say with a grain of salt, use it as advice, but in the end, make it yours. So in the end, we're going to get into our recommendations. And just a few general guidelines, so I'm not repeating myself the whole time. If your usual applications tend to be consistently similar in size, so they're always around the same, same size, you're not really getting too big or too small, then select lights that are optimal for the largest field of view that you use. So if you have, you're typically they're around 150 millimeters, then get lights that are about 200 millimeters in size. So they're slightly bigger than your field of view so you can get that uniformity. Also, in most cases, choose larger lights. It is much easier to make a larger light smaller than it is to make a small light larger. The ability to block off light and see, okay, this is a 200 millimeter bar light, but if I cover up 50 millimeters, I still have a uniform image. I can order a 150 millimeter bar light and it'll still be useful. So you can kind of figure out what the smallest size light you need, even though the light in your lab is larger. And then if you can only select a few lights, maybe you're budget friendly or size friendly, pick ones that can be a little bit more versatile. So for example, a flat dome light, you get more versatility in your working distance than you do with a standard dome light. So it's kind of, if you can only pick between the two, I would probably recommend a flat dome. A flat dome light could also be used as a backlight in some scenarios, just shining light up in a panel light. So kind of taking that into consideration of what lights might be multi-purpose if I can't get everything on my wish list to start. So on to the lights that we recommend when it comes to bar lights. For the floodlights, we recommend the FE Flex 2, 400 millimeter size, white, and the kit version. So the FE Lux lights are really useful because they are what we consider flexible. You can actually take the end cap off and slide out the lens and bring it further away or closer to the LED and change the emitting angle of the light. So instead of having to order, FE Flex 400 wide, standard, and narrow, you can get all three of those options within the same light, and you can set whatever emitting angle you need based on what the application needs. And then the kit means it comes with 3 windows. So it comes with a transparent window, which does not provide any uniformity, but it does let through all of the intensity. The semi-diffuse window, which is what a standard bar light diffuser is, gives you some uniformity, but you maintain intensity. And the opaline window, which is essentially a backlight level diffuser. So you lose a lot of intensity, but you gain a lot of uniformity. So by getting this 400 millimeter kit, we're able to make about 12 lights. Most of the time we don't recommend 400 millimeters. It's kind of larger than we typically use. We usually use 300, but the 400 millimeter just gives you that extra cushion for maybe a slightly larger application. Also the ability to line up 2 400 millimeter lights and get an 800 millimeter light versus 2 300 and get only a 600 millimeter light can be really valuable if you do have a lot of larger field of view applications. Accessories that we recommend is getting the polarizer for this light and then also getting this line scan film. So what this line scan film does is it polarizes the light only in one direction. So you would set up the light to have the most narrow emitting angle that you can, and then you add that line scan film. And this is great because it will either make a line scan light if that's what you're trying to do, but it also creates a really intense flat sheet of light, which can be really great at a low angle but large field of view application if you have something like that. So having this whole setup is that's what we would recommend for kind of getting the flood bar lights for your lab. When it comes to the precision lights or precision applications, the LDL2 is what we recommend. So we chose a 218 by 30. You can go smaller in the length if you want, especially if your applications don't usually get to be that large. The reason we chose the 30 instead of the 15 is because you can cover the light up. You can get some black cardboard, cover the width of the light in half, and then you can find out if you need to purchase the 15 millimeter light or if the 30 will work, or if it's the 30 millimeters is hiding the defect. If you have the ability of your lab to add more bar lights, then please add more 15 millimeter bar lights. It makes it easier to not have to cover up a light when you're testing an application. But if you're just trying to get the basics and just to start off with, this is a time where going larger makes it better that you can go smaller. The optional accessories that we would suggest for this are the diffuser to give you more uniformity and the polarizer. So the polarizer, I've got this N-VE here, which means dash in the vertical direction. And this only comes in handy or is necessary if you have 4 bar lights around your application and you're using a polarizer. If you use the same polarizer on all 4 bar lights, then the polarizer on the lens will only ever be perpendicular with 2 of them at a time. So in order to make the polarizer on the lens perpendicular with the polarizer on all of the bar lights. Two of them, the ones across from each other, have to be horizontal, and then two of them across from each other have to be vertical. And that way, all of the light in that square is being polarized in the same direction, so we can line up the polarizer in the lens to be perpendicular to that. If that's the case, you might want to update the quantity to 4 if you've got the budget and ability to do so. Next, we're going to talk about the ring lights. So a best flood ring light we have is the FE ring. It's the same as the FE Flex, where you can adjust the emitting angle and the kits that come with all the windows. And we recommend having the polarizer for that as well. Next, we recommend the HPR2 series. We recommend 2 of these lights. And the HPR2 is really convenient because it's a multi-angle ring light. When it's at a short working distance, it works like a low angle ring light, and as you bring it further away, it is more of a bright field light. So we recommend, and this light is great because it comes in standard as a full color option. So having the HPR2 100 full color is good because you've got that small low angle light, but the 200 will also give you the larger low angle light, so you're covering your bases there. Full color will let you test the wavelengths pretty easily, but we still have the larger ring light, the HPR2 in white, to test for different sizes. The low angle and low angle 1 lights, the LDR2 series or LDR series. The low angle lights are 3 LEDs that are at a slight angle. So they have low angle properties, but they also have more light kind of in the vertical direction, versus the low angle 1 series is where it's just 1 LED at a 0 degree orientation to the sample. So it's going to be the most low angle light that we have. In your lab, you're going to want both of these series for sure, and even multiples of the series. If you can, again, pick the light size application that you typically have, and then a few lights that are bigger than it and smaller than it. So if you can get a few of them, we definitely recommend it. But if you can only get one, maybe try and get one larger and then one smaller, so you're kind of covering your bases as best you can. And then maybe this is the first light that you grow as you expand your lab. And then the last ring light that we recommend is the LDR2 120 in white. We recommend getting a diffuser for that to add more uniformity, and a polarizer for that to be able to polarize the light. And then this adapter right here attaches the polarizer and the ring light, or polarizer and the diffuser to the light. So that's what we recommend for ring lights in your lab. For dome lights, we recommend the standard dome light, the HPD2 200 full color. And the reason why we picked the HPD2 200 full color is because it's the same size as the HPR2 200 in white. And a cool thing about these lights is you can actually swap the dome shell with the ring light. So I could create an HPD2 200 full color or white, or an HPR2 200 full color or white. So you can kind of get 4 lights out of just purchasing 2. They have to be the same size for that to work, of course. So if you don't go with 200 for each of those, you go with different size. Just make sure you get the same size between the 2. For the panel light with the camera hole, we recommend the FE flat dome. So the size for this one's a little bit trickier, and it has a lot to do with the field of view of most of your applications. If you have the most reflective sample that you could find, essentially a mirror, in order to have a uniform image across the whole setup or the whole mirror, the light has to be twice the size of the field of view. As your sample becomes less reflective and more diffuse, or as your light working distance gets closer to the part, that 2 times the size of the field of view can be relaxed. It's usually 1.5 times, something like that. But that being said, it is better to have a larger flat dome light in this scenario than a smaller one. You'll just be able to solve more applications a little bit easier. So we recommend the 300 by 300. That's kind of the one where it's still easy to hold up and mount. You can still solve most of your applications. A 500 by 500 we have in our demo inventory you can always borrow, but it's a hefty light. So Unless you're always testing large field of view applications, this is a good kind of medium size to optimize usefulness, but also, how many applications you can solve. And we do recommend getting the polarizing kit for this as well. And then when it comes to the flat dome light, the LFX-V, we recommend the 200 SW. Kind of the same thing. 200 is a little bit bigger than you need, but better to have the extra size than to wish you had bought a larger light. All right, when it comes to the coaxial light, we have a few different coaxial lights in our lineup, and the difference between them is essentially how well they work with high resolution images. So the LFV3-G has a slightly thinner half mirror to work better with, images that are taken with like 20 megapixel cameras. And then we also have the LFV3C or LFV3CP, which is good for really small field of view applications with like really specific telecentric lens. It uses a beam splitter instead of a half mirror, so you're able to get a clear image with really high resolution photos as well. Most of the time in lab, those aren't necessary. So for this lab setup, we just recommend our standard coaxial light in the 100 millimeter size in white. And the cool thing about this lineup is that the coaxial, the LFV3 series, you're actually able to take off a portion of the light or a portion of the light, and you can put in either a polarizer or light control film to give it more collimation with the light control film or remove glare with a polarizer setup. So we do recommend getting the accessories for that as well. And then when it comes to backlights, you don't need that much. CCS has the FE backlight. We recommend the 300 by 300 again, just, in terms of optimizing the size and the usefulness. And optional accessories for that, we recommend getting the polarizer as well, so you can use it as a panel light in a bright field application, but also getting the light control film kit, so you can have the, each direction you can test with both, or with one at a time. CCS does offer other backlights. There's the TH2 and the LFL. And the TH2 and FE backlight are very similar. They're both backlit LEDs. So you don't necessarily have to have both, but if you are testing with the FE backlight and you know that the backlight works, but your customer has restrictions in terms of, the size backlight they can fit in their lab, just know that the TH2 does exist. It's, half the size, if not more. And so then you would order the TH2 to fit their scenario, but the principle of the backlight between the two lights still applies. They're both uniform backlit backlights. So maybe when you grow your lab, get some TH2s, but just to start with, you can start with the FE backlight. So when it comes to wavelengths, especially UV, I mentioned when we talked about it that you want the pure UV technology built in. So we just recommend getting two 100 millimeter wavelengths. If you have the extra budget and you want to step up to 200, by all means, but make sure you get two for the extra intensity and uniformity. You don't have to, I guess, but it's kind of, the intensity of a UV light is much further along than it used to be, but it's still not nearly as bright as a visible spectrum light. So, in a lab, we usually end up having to use two at a time. When it comes to IR, this is a long list, and I am not saying that you have to have each one of these IR lights to start. So with IR, it is possible to determine the best form factor using a visible light and then using the IR light to confirm which wavelength is best. I kind of talked about that on the IR slide as well. So, in this scenario, if you get the LFX-V, then you can use that as a backlight, and you don't necessarily need to get this LDL 100 by 100 IR backlight. But then if you don't plan to get the LFX-V, then make sure you get the FE ring light so you can test the 850 nanometer wavelength and you don't just have two 940s. So this is kind of one of those where start with 1, 2, maybe 3 of them, and then grow as your lab grows and as your need for IR light grows. But you don't, like I said, don't have to have every single uniformity for this scenario. And another example of having a long list, but I'm not recommending everything, is the controllers. So in your lab, you want a good way that you can plug the light in and have an easy way to control the intensity of the light. So you can make your application solving easier. The PD310024, that is really nice. It's an 8-channel controller and it can do the standard 24-volt lights, but it can also do the HLV3 current-driven lights. And it's got really easy intensity control. You just turn a knob to make the light brighter or not. It is a little bit of an older controller, and I say that only because we did come out with the PD4, which is, a little bit more powerful. It's only 4 channels though, and you can't do the HLV3, but it does have really easy intensity control on that one as well. Neither one of these controllers do overdriving, so if you're going to pick the PD3 or the PD4, then you also want to get a good overdriving controller. We just chose the RT420-20. The reason for that is so you had four channels to work with. So if you were trying to overdrive 2 bar lights at the same time, you didn't have to set up 2 separate controllers. You could just use two of the 4 channels. There's, kind of more that goes into picking the right overdriving controller. So if you have a lot of high-speed applications and you really want to make sure you're picking the right thing, please reach out to us and just, we'll chat with you and say, okay, and maybe in your scenario, we don't need the RT420, we need something else that we would recommend. So if you have a question, just please ask us. And almost last but not least, but the CDVA series. This one is a cool controller because it has 4 channels, but it also is modular where you can just add another module to it, and it's got IR communication, so as long as they're close to each other, they'll talk to each other. So you can make 8 channels very easily with just buying another module. The only downside to this light is it's limited to 50 watts per channel. That being said, in terms of a downside, none of the lights I recommended in the lab are above 50 watts per channel. But if you have those high-speed applications, or large field of view, then you're using larger lights, you might get to that point where you're kind of at a light, trying to test a light that is more than 50 watts per channel. So if you tend to use more powerful lights, this might not be the best controller for you. The benefit of it is it does have overdriving capabilities built into it, so you don't have to get the dedicated overdriving controller. Another maybe downside, it's up to you, is it does use DC power, so you have to have a power supply to turn it on. And then actually, last but not least, to power the FELux lights, we recommend the FES power. It just plugs into a wall and gives you one M12 connection that you can plug your light into, and your light will be on. Otherwise, FELux lights do work by plugging them directly into a power supply, and then you have a little bit more control with the pinout as well. So if you don't want to get a dedicated FELux controller, you can just get a power supply for the lights instead. And then one thing to note, my kind of caveat to this, is these are lab recommendations. So this is what we think is going to make your testing in your lab the easiest. But once you are testing your lab and you choose the configuration you need, the size of the light, the quantity, etc., pick the controller that makes the best sense for that configuration. Just because you tested with the PD310024 does not mean your low angle ring light needs to have that controller. It could probably get away with a much smaller one for a lower cost. So make sure that, after you have all of your lights chosen, go through and then choose the best controller you're going to sell in that scenario. So now we're going to get into kind of lighting equipment that we recommend. That's not necessarily lights or powering the lights. The first one I've touched on is the filter kit and getting a good machine vision filter kit. The minimum that it should have is a red, a green, and a blue bandpass filter with a UV cut filter. More is good. Like I said in the wavelength slide, if you want to test and see if a cyan is the best color, you need a cyan filter. So if you have that, that's great, but these are the most common that you're going to need. You also have to make sure that it has a good polarizer in the filter kit. And then another just kind of idea is make sure that it fits most of your lenses. It's really, really annoying when your filter kit doesn't fit the lens that you're using and you have to kind of hold it up and you can't just screw it in. So either buy a filter kit that's perfect for the size lens you have, or get some good step up, step down rings so you can twist it in if you need to. What we have in our lab is the Midwest Midwest Optics FK201. I like that one a lot because it's not overkill, but it covers all your bases. So for me, that's a good one to have as a kind of basic filter kit. The other equipment that we recommend is getting extension cables. So for precision lights, the FCB cable, just the FCBX, pick whatever length you want. For a lab, you can probably do 2 or 3 meters is going to be plenty. And that's just your straight cable, so that will connect the lights to the controllers, whatever controller you pick. The FCB-F-X is a 4-branch cable, so one cable will go into a controller, and then you can plug 4 lights into that cable. That's probably the best for a full color light, because then you're not taking up 3 channels trying to plug in the full color light. You're only taking up 1 channel. These are, optional as well. If you don't think you want it, then you don't have to have it. And then last but not least is a flying lead cable. And this would go between the CCS lights and like a power supply, for example. We actually don't really recommend plugging our lights directly into a power supply. They don't really have the built-in driver that an Effilux light has, where it's like meant to do that. So I don't really recommend going with this, but if you did want to do that option, this would be the cable that you needed. For the floodlights, the cables you're going to want are this long part number here, the FE-CAT, CAB, M12, female to male, whatever length. Again, 2 meters is probably fine just for your lab. And this would be for connecting the Effilux lights to the FES power, where it has that M12 connection, or smart cameras, something along those lines. If you do want to plug in your Effilux lights to a power supply and have more control over the wiring and cabling, then you would want to get the flying lead version of that cable. So those are the 2 kind of different cables for the different applications you have that we would recommend. And we're getting there towards the end here. That's essentially everything that we have in our lab that I think are the basics of, having the right lights, being able to power the lights, and having the flexibility with the cables. So now I'm just going to touch on other things we have in our lab that are useful to us to help us solve applications. So this isn't necessarily lighting related, but more just general good things to have in your lab. The first one is if you have to imitate a conveyor or texture. Sometimes this comes up where I have to make sure that my light or my image isn't going to be affected by having my sample sit on a conveyor. I actually bought shelf liner from the hardware store, and that worked really well to just kind of provide some texture as my background so I can double check that it won't be a problem once it's installed on the machine. We also recommend having clear acrylic sheets for backlight testing. It's very rare in a manufacturing scenario that the light or the sample itself is going to be sitting directly on a backlight and then be able to go through the process. So you don't want to test your sample sitting directly on the backlight, because as we learned about in collimation, as we move the light further away, it will change the image as we move it further from our sample. So what we have in our lab is clear acrylic sheets that we'll set up on blocks, and then we'll put our sample there, and it can be in between the camera and the backlight, but not have to be sitting directly on the backlight. So that works really well, just to make sure you're getting the same image in testing and the same image when it's actually installed on the manufacturing line. We also have a lot of black poster board, and this is kind of what we cut to size as needed to make the lights smaller. So that's where we're buying larger lights, blocking them off. You need something to block them off with. Another little trick, the privacy film, like a 3M screen, privacy screen that you put on your computer so no one can read over your shoulder, that is actually just light control film. So we'll have a few sheets of that in our lab and kind of cut it to size if we don't have the specific light control film with the light that we purchased, something like that. And it works really well. It's kind of a nice cost-effective way to be able to do that. That being said, the light control film we sell with our lights is manufactured and rated to keep up with the heat that the lights can generate. So you cannot just buy the privacy film and install that on the light and then put it on a manufacturing line, there's a strong chance that over time it will melt and deform and stuff like that. So test with the privacy film, but when you go to purchase the designated light control film that is made and designed to work with the light. You can also get a polarizer or film sheet from Amazon, and that's the same principles applies. You can cut it to size, but when you go to order it, order the polarizer that is made and designed with the light in mind. A copy stand. This is a big tool that we have in our lab, so that is what we mount our camera to. It's really easy to hold the camera in line. It can also be tilted off to the side and really easy to adjust the working distance of the camera. When it comes to holding up the lights, Bogan arms are really useful if you haven't heard of that. It can like clamp to the table on one end and the other end clamps to the light, and then you can kind of twist it and lock it in place. So once you know where you want your light to be, you can use your Bogan arm to hold it there, and then you kind of get your hands back for adjusting filters or taking images and writing out the name of them, typing out the name of them, stuff like that. Swivel Link kind of does a similar thing. The only downside to Swivel Link is it has to mount to extruded aluminum or have a mounting plate for specific lights, so it's not as flexible, but it is more sturdy. So that's kind of the pros and cons of those two. We also have a lot of blocks on hand to hold up lights, and we designed a few and 3D printed a few that we can stack in like 5 and 10 millimeter increments. So I know if I have 5 of these blocks, my light working distance is 50 millimeters. So it kind of just makes testing a little bit easier, and a little easier to, see what light working distance is optimal for my application. Last but not least, not even last but not least, but next up is UV safety glasses. Don't sleep on safety. It's not worth hurting your eyes for testing a UV application. You might look goofy, but you're in a lab solving lights. Nobody cares. Buy the safety glasses. Other things we have are the power supplies. So this is different from controllers. The controllers are controlling the light. The power supplies are essentially just providing 24 volts and however many amps you purchase. So this would power the CDVA, the Gardasoft controller, or the FUlux lights. We also tend to use extra wires, resistors, stuff like that. And this is mostly for when we're trying to connect the triggering of the camera to work in synchronization with the controller. A lot of times that's for the high-speed applications, stuff like that, but it does come up and come in handy a lot. A lab jack is essentially what you would think a car jack, but for your lab. So it's a little table that you can just kind of turn a knob and it will move the table up and down at a really fine precision control. So this is really useful if you have applications where you're using telecentric lenses and they have maybe a really small depth of field and it's hard to get your camera at the right working distance where you can get your sample in focus enough. That's when a lab jack is really going to thrive because you can just use that to do a fine adjustment of your light working distance and get it in focus. If you don't have that scenario, then you do not need a lab jack. So keep that in mind. And then last but not least on this page, we have the tools that we use. And this is tools like rulers, angle measurers, stuff like that. So we can make a note of, where we're placing our light so we can copy it in the manufacturing setting. And pretty honestly, this is last but not least, kind of to help, what questions do you need to ask to help make the decision of what lights to get for your lab? The first one is, what is my largest field of view that you're going to come across? Is that a common field of view that you have, or is it a one-off? Do you want to build your lights around that larger field of view, or do you want to build them around your average field of view? And that's a question that I cannot answer for you. That's up to you. But thinking about the field of view, and then once you decide, okay, this is the field of view we're going to use the most, or this is the largest one we always have, purchasing lights that are slightly larger than that so you can get the most uniformity. The second question is, what applications do I see the most? We've talked about this a lot. If it's small defect detection, get precision lights. If not, get floodlights. Do your samples vary a lot in terms of reflectiveness, color, texture, stuff like that? If they do, then you need a large variety of lights. If the samples are pretty consistent, then you can kind of pick the kind of few lights that are really good for highly reflective samples. For example, you can get more of those. You don't have to focus on a dome light as much, something like that. And then the last question is, are there any applications that I haven't been able to solve? Maybe that's something where I didn't know I needed to add a light control film to my coaxial light, and now that's new information I can try again. But is there anything that we haven't been able to solve that maybe having a different light or accessory will help us with? But in the end, that is our webinar. So we'll move on to questions. And thanks for your time.